last time we mentioned about light can be polarized when the light goes through a certain like material that's made of Polaroid, the kind of material we call a Polaroid. And that is, when light, initially when you have light, that's a, take for example, you have light initially that is unpolarized, which we use this, the X and Y axis to indicate it's unpolarized light. And when it passes through the polarizer, for this one, the polarizing axis is in the vertical, so you can see that the light, half of the light will be screened out. So only the light that's in the same direction as the polarizing axis will remain, and also the intensity is dropping by half. And then let's say if we place another polarizer in front of this polarized light, what's going to happen is that the light intensity is going to be further reduced, and the directions of light will be in the same direction as the polarizing direction of the second one. And how does the light intensity behave when it passes through a polarizer? So if you have an already polarized light, then the intensity of light passing through the second polarizer will be the intensity times cosine theta squared, and that we covered that yesterday, 2 days ago. So let's see. Hold on, let me just stop the pointer. So now we're going to, the next thing we want to go over is that what happens to light when you have light that's propagating, through the air, and let's say the light, striking on the surface, and that material is made of is different from the air. Then how would light propagate through different media? So that's a question. That's the topic. That we are interested. So when you have light, take for example, using this diagram, you can see that this is light in air, and then this is light travel in air, and then when it encounter the interface, this light we call an interface, and this, let's say this is a material that's made of glass, which of course will have a different property than air. Then when light goes through, propagated through air and striking at that point, what's going to happen is that the light is going to split in two directions. One that's going to be reflected. So once it strikes the surface, it's going to be reflected. So we call this reflected ray. And this one, the other light ray is going to be propagating through the material. And this light ray we call that refracted light ray. So you can see that when you have something like this, usually we would draw a vertical line to indicate that is perpendicular to the interface, and we call that line as normal. So in other words, let's say this is the interface, and so you draw a line that's a reference line. This line we call that normal. Okay, and so you're going to have a light ray that's incident propagating through through air. So let's say this is let's say some material that has an index of refraction, we call that N1, and then you have another material that has a different index of refraction, N2. So when light propagates through different material that has a different index of refraction, what's going to happen is that you have you have the incident. This is what we call, this line is called the rate of incidence, and then once it strikes at the interface, this light ray is going to be reflected. Okay, so this so this is what we call the law of reflection, which is right here. So what does law of reflection tell us? The law of reflection says that a reflected ray lies in the plane of incidence and has an angle of reflection equal to the angle of incidence. So that's this is angle of incidence. That's called theta 1. So the angle by law of reflection, we know that this angle has to be the same. So let's say if that's theta 1 prime, then the law of reflection says that your theta 1 has to be equal to theta 1 prime. So this is what we call law of reflection. And that's so common sense that, but so we call that law of reflection. Yes, Molly. How do I, hold on. Raise your hand, yeah. You can speak, I think. Okay. Can I let you speak? I don't know. Let me see. If you raise your hand, how do I let you? You know what? Just type your question. Where are the angles measured from the perpendicular line? Okay. Why are they measured in perpendicular line? That is because we use, this is our reference line, so we call this normal. Oops, normal. So this is how the light ray propagates. You go this is the interface. It strikes at the point, and so the angle is in reference to normal. That's a good question. It is in reference to the vertical line, not in reference to to the horizontal axis as you are used to. So this is what we call low reflection. Does that answer your question, Molly? This is all right. So in other words, the angle. So this theta 1 we call that angle of incidence. Theta 1 prime we call that angle of reflection. So angle of incidence is equal to the angle of reflection. That's basically what this equation tells you, and it follows the law of reflection. And the angle is measured from the normal, not from the other axis. Now, the other important law in optics or about light ray is the law of refraction. And this one is what we call the Snell's law that deals with the light propagating in different material. As you can see, this is reflected. The reflected is in the same medium, as the incident. But then for the reflected, let's say you have something like this. Okay, and we call this angle theta 2. Again, you can see that this angle is measuring against the normal, not against the horizontal line. So by law of refraction, it says that sine n1, which is the index of refraction, n1 sine theta 1 is equal to n2 and then sine theta 2. So this relates how light ray propagates through different media. And so it's basically you have n1 sine theta 1 that's equal to n2 sine theta 2. And so you might ask, what is n? So we haven't defined our index of refraction yet. Now, as I mentioned on Tuesday, the index of refraction basically is the ratio of the speed of light. So let's say your n is defined as the speed of light in vacuum over the speed of light in the medium. Okay, in the medium. So you have n, that's c, that is your c over v. Okay, so this is the definition of index of refraction. So you can see that, as we mentioned earlier, the light travel in air definitely is different from the speed of light travel, that's in glass or in water. So how do we quantify the index of refraction? Basically, that is based on this equation. Okay, if you measure the speed of light, find the ratio, then you can find the index of refraction. Now, speaking of law of refraction, this is the equation we follow. So it's very straightforward, and this is a diagram that shows you that the angle has to be measured from the vertical axis. Any questions so far? Okay, so I'm going to turn to the next page. So when it comes, let's see, and then, okay, I'm going to stop. So when it comes to the light propagation, this one shows the example. So maybe I should just enlarge this. Okay, so if you look at the light, and if we are interested in studying how light propagates through different medium, media, then you can see that this is what we call normal. So whenever you have an interface, this interface is is a surface between different materials. So you have N1, you have N2, and you have light that's propagating through the first material, and then when it's striking the interface, this is the reflected rate, this is the refracted rate, and the angle. This is angle of incidence, this is angle of refraction. So let's look by using Snell's law. Let's look at how light propagates. Let's say if we have a case when both N1 and N2 they are the same, which means that they have an index of refraction. What's going to happen to the refracted rate? What's going to happen is that because your N1 is equal to N2 by Snell's law, because your N1 sine theta 1 is equal to N2 sine theta 2. So if you have N1 and N2 exactly the same, from this equation, we know that your theta 1 and theta 2 has to be equal to each other. So what does that mean when theta 1 and theta 2 are equal to each other? It means that the light ray will not be deviated. It will just just go straight through the material, second material, okay, without deviation. Now let's look at this scenario when you have N2 that's greater than N1. So in other words, you have a light source initially in a medium that has a lower index of refraction, and then when the light propagated through through the second material that has a higher index of refraction, then what's going to happen is that because N2 now is greater, if this is larger, if N2 is larger, then because everything has to, and if this is larger, which means that your theta 2 has to be smaller, just so that the product of these two quantity will be equal to whatever on the left hand side. So what's going to happen is that if theta 2 has to be, so in this case your theta 2 has to be smaller than theta 1 if N2 is greater than N1. So just by looking at this, if your N2 has to be less than theta 1, it means that the refracted rate will be closer to the normal. Okay, so this is how you judge how the light ray propagates through different media when they have a different index of refraction. So light ray propagating from the smaller index of refraction into a material that has a higher index of refraction, the refracted rate will be closer to the normal. Now let's look at the third scenario when you have N2 that's less than N1. So in other words, now you have a light source that initially started in a medium that has a higher index of refraction. When it propagates, when it's striking the surface, it's going to be refracted. Now by using the same argument, when N2 is smaller than N1, then theta 2 has to be greater than theta 1. So what does that mean? So in this case, your theta 2 has to be greater. Your theta 2 is this. Your theta 2 has to be greater than theta 1. It means that the reflected light ray has to be away from the normal. Okay, so if N2 now is less than N1, so you have the theta 2, so you have your theta 2 greater than theta 1. Okay, so it's basically, so you might ask, let's say in this scenario, you have like light that's traveling from air to glass. So you'll find that the refracted rate will be closer to a normal. So in this case, let's say you have the light source that's actually embedded in glass, and then it's propagating through the glass and striking through the interface and into the air. Then the light that's being refracted will be away from the normal. Okay. So this basically describes how the light ray will propagate when it is going through different media. Now let's look at this case. Let's say when you have a different light ray, what's going to happen? Okay, I mean, if you look at the stuff here, let's see. So if we look at the color, okay. So another one that we're going to talk about is actually just give you a very brief descriptions about what dispersion is about. What is dispersion? Dispersion basically describe. This is too painful to write, so I'm not going to write. So dispersion. What is dispersion? Dispersion basically says that different wavelengths are reflected at different angles. What does that mean? Different wavelengths are refracted at different angles. We know that when we look at visible light, the visible light does not have one single wavelength. The visible light actually consists of waves of different wavelengths. You see the red color, you see the green color, you see the blue color. So all these color indicate that the light ray, they have a different wavelength. So when you have a light ray of that composed of waves of different wavelengths, when it go through, when the light go through different different media, then the light ray will be refracted. That we all know. But then different color of light ray will be refracted differently, and that is because the index refraction is the function of wavelength. So in other words, the index refraction, we know that is a ratio of speed of light. In addition to that, the index refraction is equal to let's see, do I have that? Is actually a function wavelength. So that's we just write it like that. It's a function wavelength. And from this picture, from this diagram, we can see that when you have light ray that's going from, let's say from air to glass, from low index of refraction to higher index of refraction, what's going to happen is that you see the blue color. The blue color is refracted close. The angle of refraction for the blue color is smaller than the angle of refraction for the red color. So in other words, the red color will be away from the normal greater than greater for the blue color. However, if the situation is reversed, let's say the light source is from the higher index of refraction to a material that has a lower index of refraction, what's going to happen is that you find that the blue color is actually being refracted further away from the normal, and the red color is actually closer to the normal. Okay, so it really depends on where the light source is located. You get a different dispersion. You get this one, the red is closer. The red is away from the normal, and this one, the red is closer to a normal. And all this, of course, can be found by using the Snell's law, which is n1 sine theta 1 that's equal to n2 sine theta 2. Okay, so that's that. And so the next one we're going to talk about is that when you have light ray that's propagating through different media, what's going to happen is that some light may not be able to be refracted. So in other words, let's say let's say you have the interface like this. So this is our interface, and then this one we have, let's say N1. Okay, let's see. We want to be consistent with. So let's say this is what we call N1 now. Okay, and this is what we call N2. Okay, so in this case we know that because this the lower part is actually in color, which means that it has a higher index of refraction. So the prerequisite here, the situation we have here is that N1 is greater than N2. All right, so what does that mean? It means that now, let's say if we have a light source that's placed in this second medium, in N1, in the N1 material, and so the light is going to produce this light source is going to produce light in all directions. So we want to follow the light ray just to see how they behave when they encounter when they striking the interface. Let's look at the most simple one. If we have a light ray coming from the light source that is directly perpendicular incident on this interface. Now I'm going to draw a line that's indicate the normal. What's going to happen is like when you have light ray that's incident perpendicular on the interface, this light ray does not deviate. It will just directly propagate because there's no angle, there's no deviation, so it will just propagate like that. So let's say so again, whenever you draw this, you have to draw normal as your reference axis. So now let's say we have a light ray that's going from this point. It's making an angle of incidence. Okay, so this is angle of incidence. That's angle of incidence, and then going through the second material. Now, so let's say this is your theta 1. If this is a theta 1, so how would the angle of refraction? How would the angle of refraction be? Is it going to be larger than theta 1, or is it going to be smaller than theta 1? So so this is my question to you. If you have a light source that is embedded in a material that has a higher index of refraction, now we have an angle of incidence that's called theta 1. Will the angle of refraction be larger than theta 1 or smaller than theta 1? So in other words, will it be closer to the normal or away from the normal? If you just do that by Snell's law, if n1 is large, then what is the relationship between theta 1 and theta 2? Is theta 2 going to be larger than theta 1 or smaller? Smaller? Which one is smaller? Theta 1 or theta 2? If n1 is larger than n2. So my question to you is theta 1 larger or smaller? Hello? Theta 1 travels slower. Well, light travels, n1 has a higher index of refraction, so it travels slower. So that's why so n1 is c over v. So if n1 is larger, which means that it does travel slower. But then I'm asking whether the theta 1 is greater than theta 2 or not. All right. However, let me write down this. Let's go back to the previous slide. Okay, we have a situation now that n1 is greater than n2. If n1 is greater than n2, so what does that mean? If n1 is greater than n2, it means that theta 2 has to be greater than theta 1 just by using this equation, right? Okay, so what is the answer? The answer is theta 2 is greater than theta 1. What does that mean when theta 2 is greater than theta 1? When theta 2 is greater than theta 1, it means that theta 2 is going to be away from the normal, right? Much greater than theta 1. So you would expect the refracted ray, let's see, greater than that. So let's say like this. Okay? So in other words, you have a light ray that is greater than, your theta 2 is greater than theta 1. Okay, so this is when you have a light ray like that. Now imagine the case that if you study the propagation of light ray for every single light ray, with a progressively larger theta 1. When theta 1 gets larger and larger, we know that theta 2 is going to get even larger and larger. So what's going to happen is that there's going to be at a point. So let me draw a vertical line here. That's my normal. So let's say a certain angle. When this line rate, so again, this angle, that's called a theta C, the critical angle. When the light ray that is striking at the interface at a critical angle, what's going to happen at the critical angle for light ray is that the refracting ray will propagate along the interface. Okay, so this angle is what we call the critical angle. As you can see just by looking at this picture, if you look at this picture, because we mentioned that when the theta 2 has to be greater than theta 1, and then we can progressively enlarge our angle theta 1 so that our theta 2 is going to be progressively larger as well. And so there will be a point that when the theta 1 is equal to the critical angle, the light ray is not going to be reflected into the second material. It's actually going to propagate along the interface. Okay, so this angle, when the light ray that's being reflected and propagate at the interface of the two different material, we call this angle the critical angle. So the critical angle, is the angle that is in a higher index of refraction. So what is the value of that critical angle? How do we figure that out? Okay, so by using Snell's law, let's look at what the critical angle is. We have N1 because N1, and then we have sine. This is very difficult to write. We have N1 sine theta C. Okay, that's equal to, now for this refracted ray, this is still what we call the refracted ray, that's equal to N2, and then sine of, what is the angle of refraction then? What is the angle of refraction? That's my second question to you. What is the angle of refraction? In other words, what is our theta 2 now? 90 degrees, exactly. So this angle measuring from the normal is 90 degrees. So that's your 90s here. Okay. So what we have here is that if you apply Snell's law, you have N1. So N1 is here. So N1 sine theta C, which is sine the critical angle, that's equal to N2 and then sine of 90 degrees, because now the light ray is propagating along the interface. So rearrange this, you find that the critical angle can be calculated if you use the it follows this this equation. So N1 sine theta C is equal to N2 sine 90 degrees. Okay, and so theta C has to be is equal to the inverse sine of the ratio of index of refraction. So in this case, in order for this equation to be mathematically correct, N1 has to be greater than N2. So what does that mean? It means that in order for the critical angle to exist, then your N1 has to be greater than N2, and which means that the light source has to be initially embedded in a material that has a higher index of refraction in order for for the critical angle to exist. In addition to that, let's look at a case. What happened to, so we find that when the angle of incidence is equal to the critical angle, the refracted ray is basically propagating along the interface. What will happen if we have a scenario that the angle of incidence now is even greater than the critical angle? What's going to happen to that? When this, let's say this is just the angle theta. So the angle theta now is greater than the critical angle. So if this angle is greater than the critical angle, do we expect any refraction at all? Do we expect any light rate in this material? Do we expect any light rate in that material when the angle is greater than the critical angle? Yeah, me too. So I don't think so, because the most that the refracted ray can do is propagate along the interface. When you have the angle that's greater than the critical angle, what's going to happen? The refracted angle just now is 690. Well, if you say that it's 690, actually it goes like this. So it follows the lower reflection. Okay. So what we have here is that when you have, let me get another slide. When you have angle that is greater than critical angle, then total internal reflection occur. So in other words, we do not expect any reflected ray. All the light ray will be actually being refracted back and reflected back into itself. Okay, into the median itself. So this is what we call the total internal reflection. And we actually use this technology for, or this this principle for a lot of things. For example, I hate to use mouse. It's so difficult to write. Total internal reflection. Let's say the fiber optics that we heard fiber optics. How does it work? So basically, you have a channel. So this is fiber optics. You have light ray that just actually propagating within that channel. It is not, well, to the edge. Okay, so it's not, so nothing outside. So light just propagate through this guiding channel, and basically the physics, the physical principle at work is the total internal reflection. So information can be propagated through this channel without escaping to different material. So just by looking at this picture, we know that the index of refraction of this channel or the guiding channel has to be greater than its surroundings, so that the total internal reflection can occur. Okay. Any question? All right, so let's move on to the next important concept, which is polarization by reflection. Okay, now we mentioned that when you have unpolarized, previously we mentioned that when you have unpolarized light coming at you, the light is unpolarized, but we can polarize the light by placing a Polaroid in front of the unpolarized light. And what's going to happen is that when the unpolarized light going through the polarizer, light will be polarized. So in addition to using a polarizer to polarize light, there's another way to polarize light, and that's actually, it just happens, if the angle of incidence happens to be some angle, then the light will be polarized. So let's see, how does it work? Okay, so let's say this is the interface. You have two different materials. So again, I'm not going to use the I'm just going to use the N1, N2, because that way you're not limited to yourself as air and glass. Okay, so let's say this is your N1, this is your N2. Whenever you want to study the light propagation, you have to draw a vertical line to indicate your reference line. Okay, so what's going to happen is that that's initially you have a light ray that's unpolarized, so that's incident at this location. Okay, so because it's unpolarized, so what we're going to do is that, remember, unpolarized light, we use the X and Y axis to indicate that's unpolarized. So I'm going to use, since this light ray indicate the directions of wave propagation. So the only two ways of the the only two directions for the electric field and the magnetic field would be one that is into or out of the whiteboard. So I'm just going to draw a dot, and the other direction is like up and down, up and down. So in other words, you have a unpolarized light that's oscillating in and out of the whiteboard, and also in this direction, and light ray is traveling in that direction. Okay, so just by looking at this picture, we know that this light ray is not polarized. Okay, so as I mentioned, when this light ray incident at a certain angle, we found that the reflected ray is actually polarized. Okay, so this angle, we call that Brewster's angle. So that's called a theta B. Okay, so theta B. So as I mentioned, so reflected by the lower reflection, this angle has to be theta B as well, because they are equal to each other. And also, we found that this reflected ray is polarized. Alright, so which direction of light will be absorbed and which direction of light will remain? We found that the light ray that's into and out of the whiteboard remain, and those that in like oscillate in this XY plane will get absorbed. Okay, so unpolarized on this side, once it being reflected, it becomes polarized on that side. And then what about the refracted ray? By Snell's law, we know that it's going to be refracted. Now, because let's say N1 and N2, if we assume that N1 is has a smaller value and N2 has a higher value, which means that your theta 2 will be in a direction that is the angle theta 2 will be smaller than theta 1. And if the theta B, so theta B, so what will be the directions of the refracted ray? We found that when the angle is incident at the Brewster's angle, this is a refracted ray, and we found that this two is satisfied this equation. This two angle has to be 90 degrees. So this is our angle refraction. We call it theta 2. So if this angle and that angle add up to 90 degrees, what will be the relationship between the angle reflection and the angle refraction? So in other words, theta B and theta 2 will be what? This is the vertical planes, right? So that'll be theta B, and so in other words, your theta B plus the theta 2 will be equal to 90 degrees, right? So in other words, your theta B you know what, let me just use this. Your theta B plus theta R. So theta B is this angle, or this angle, because they are equal to each other, plus theta R, which is angle refraction. It has to add up to 90 degrees because this reflected ray and the refracted ray are perpendicular to each other. This happens only when the angle of incidence is at a particular angle, and that particular angle is what we call the Brewster's angle. Okay, so theta B plus theta R is equal to 90 degrees. Now, before we move on, so before we apply Snell's law, the other thing I want to mention is that if you look at the this diagram, you can see that the reflected ray is polarized. However, the refracted ray is not. Okay, it's still unpolarized. Okay, only this reflected ray is polarized. So now we are ready to apply Snell's law and just to see what we get. So let's say you have N1. So you have N1 and then sine theta B. That is equal to, in this case, you have your N2 and then sine theta R. And You know what? Let's just use this. So you have n1 sine theta b that's equal to n2 sine theta r, and then we're going to express our theta r in terms of theta b. So theta r is equal to 90 degrees. So your theta r is equal to 90 degrees minus theta b. So you have n1 sine theta b that's equal to n2 sine and then theta r, which is 90 minus theta b. So what is sine of 90 minus theta b? That will just give you cosine. So you have your n2 cosine theta b. So in other words, you have n1 sine theta b that's equal to n2 cosine theta b. So now they have the same angle. So you can find out what that angle is, and that angle is basically the inverse tangent of n2 over n1. Okay, so that is this is how you find the Bruce's angle, okay, which is, so I would just say theta b theta b is equal to inverse tangent inverse, all right, you know what, theta b is equal to the inverse tangent of n2 over n1. Okay, all right, any question? I mean, the mouse used to be okay to use to write stuff, but I don't know. I mean, the updated version is just not very easy to use. All right, let me see. So basically, we finished this chapter 33, and you have the. Do we have any question? Nope. Okay, so I'm actually just going to stop the recording, so it's not to does not take out a lot of memories and stuff. Stop.